All right, good morning, everyone. I think this is the last session before lunch, and we have two interesting slots. Up first, we have Nick Spinale, who's going to be talking to us about Rust support in seL4 Userspace. Nick's mentioned that he's happy to take questions during his talk. If anyone wants clarification on anything, just put your hand up, and he may call on you, and I can bring you a microphone. So thanks, Nick.
Cool. Thank you, Kent. Can everyone hear me? Cool. So my name is Nick Spinale. I'm an independent researcher and consultant out of Portland, Oregon, and I'm going to talk about Rust support in seL4 Userspace. I'm going to try to leave at least 10 minutes for questions in this 30-minute slot because I don't presume to know exactly where the interest in this topic lies. So that's why I think we have time for clarifications and questions in the middle if you all have burning questions, and there'll be plenty of time at the end as well. So just a tiny bit of review and motivation here. So as many of us are well aware, Rust enforces memory safety using compile time analysis, sometimes analysis of variable lifetimes and pointer usage, sometimes with the help of the programmer in the form of annotations. And this approach eliminates the need for heavyweight language runtime, for example, implementing a garbage collector. Quick code example here. R in the outer scope attempts to refer to X, whose lifetime is limited to the inner scope. The compiler catches this and gives us that error. And more generally, Rust aims to provide all of its higher-level language features, like closures, Haskell-style type classes, and library-level green threads, with minimal overhead, and the documentation refers to these features as zero-cost abstractions. And thanks to these design decisions, Rust is suitable for use cases from microcontrollers to the server and from the OS kernel to applications. About a year ago, Rust became just the second language after C inside the Linux kernel, and I take this as a signal of Rust's maturity for low-level use cases like ours, and that community support for this class of use cases will only continue to grow. So Rust is a great fit for seL4 Userspace, especially for unverified components in seL4 Userspace, because it's a high-level language that provides memory safety, the power of abstraction, and the sometimes undervalued promise of developer productivity, all even for components without access to OS services, and even for resource-constrained systems. At last year's summit, I presented a vision for how upstream support for Rust and Userspace could be designed. And thanks to funding by the foundation, I've been able to spend a bunch of time this year, or a bunch of time since then, realizing that vision. And just last week, this work that I'm going to be talking about today was accepted into the seL4 Foundation GitHub org. This work primarily consists of a bunch of Rust libraries known as crates, and these include bindings to the seL4 API, a runtime for root tasks, a runtime for microkit protection domains, and much more. There's also a CapDL-based system initializer, a general-purpose kernel loader, Rust-C target specs, examples, and tests. The repository's README outlines all of this as well and contains links to all the relevant documentation. And this work has been carefully organized into layers so that you can take only what you need and leave the rest. And that'll be a theme throughout my overview here. But that said, I thought it'd be helpful to use one of the demos as a guide for this presentation. It shows just one way to make use of all of this. It's a simple HTTP server that serves a static site over TLS. And I'm going to be talking about TLS, transport layer security, and TLS thread local storage in this presentation. I'll try to explicitly use thread local storage when I'm talking about that instead of using SSL for TLS. Yeah, and the site that it serves, as you can see, is our favorite website. It's built, this demo is built on top of the microkit, and there are 4 protection domains. We've got a driver for each of the network, block, and timer devices, and then the server itself. The server contains a file system implementation, a TCP/IP stack, and a TLS implementation. It achieves concurrency using library-level green threads, which we'll talk about later, and the network and block drivers make use of the device driver framework. So don't want to steal any of Yvonne's thunder here, but just briefly, this is how you build a system using MicroKit. You pass a system description along with your protection domain images to the MicroKit tool, which spits out an executable system image. The protection domains in this demo are pure Rust code, well, except for the TLS implementation, which is embed TLS. That's not really that interesting for this presentation, so I'm not going to talk about it unless someone asks about it later, which you're welcome to do so. And the scope of this work is more limited to just, creating user space programs in Rust, so we're going to focus on the protection domains. Let's see how we create these pure Rust protection domains. The main ingredient is, of course, our Rust code. We also need the libseL4 headers and interface description files. I'll talk more about that in a second. Finally, we need a Rust-C target specification. This is a little JSON file that the Rust compiler understands that has a few LLVM parameters and some linker flags and a little bit of other stuff. The default target specifications that ship with the Rust toolchain that you can use implicitly can suffice in some cases, but I provide some more suitable ones. But for some cases, you might have to create your own. But it's just a small JSON file. We invoke. They're a bit annoying to deal with, and later, if anyone's interested, I can talk about how I provide an example of a way to deal with the fact that they're not super documented and not super stable. We invoke the Rust toolchain to build our protection domain images. And what I want to emphasize here is how few external dependencies there are and how few moving parts there are. There's no C compiler or C runtime, for example. There's no linker script. Also, the Rust toolchain makes it really easy to manage toolchain versions and ships with a linker, so that's fewer moving parts there. All it takes to build a protection domain image is one invocation of Cargo, Rust package manager. We point to the libseL4 headers and the Rust-C target spec with environment variables. And those -z flags are out of scope for this presentation. They're not that interesting. I just wanted to include a complete invocation verbatim here so you could see how little there is to it. Now let's zoom in and talk about the Rust code itself. So the first crate I want to talk about is called seL4 sys, and it's basically a straightforward implementation of libseL4 in Rust. And this is how the C libseL4 source is generated. You've got some handwritten C declarations which have types and constants. Then you've got some object interface definitions that get, you have some object interface definitions that get, from which object invocation code gets generated, and you also have some bit field definitions from which C structs get generated. We generate the Rust source for the seL4 sys crate in much the same way. First off, basically with a few differences. So first off, instead of generating C from the bit field and object interface definitions, we of course generate Rust. And also to avoid boring and error-prone manual duplication of code, we generate Rust types and constants from the handwritten C ones. And this is a well-established technique in the Rust ecosystem. We use a tool called bindgen. That it's a very common way to do this kind of thing. And that's not translating any code, just types and constants. And then finally, we have a bit of extra glue code to fit it all together. And by the way, all the generation and all this code generation and translation is implemented in Rust, so no dependencies on Python or external build scripts for that stuff. And that's for the sake of just simplicity, both in the code itself and also from a build system perspective. The result is a pure Rust implementation of libseL4. The only build time dependency outside of Rust is the libseL4 headers, or the only build time dependency outside of Rust and the libseL4 headers is libclang. And by the way, now thanks to some tweaks to the upstream seL4 build system, the libseL4 headers now include those bit field definition files, those raw bit field definition files and object interface definition files. And as witnessed by the cargo invocation I showed earlier, building this crate is very simple, and it doesn't impose much extra work on building dependencies of this crate. All you have to do is point to the libseL4 headers with an environment variable, and all of the code generation and translation is handled by the crates build script. And notably, from the design perspective, thread local storage is optional. I'll talk more about that in a bit, because I've designed all of this to be as general and useful in as wide a variety of circumstances as possible. So Sam mentioned this earlier, but to test the implementation, we use an approach that Project Sparrow first used, which is to create a static library with the same interface as libseL4, and then link seL4 test against it and run the tests, and the trick works really well. And yeah, so that was what Sam was talking about earlier, and that comes from Project Sparrow. On top of that lower level libseL4 implementation, we have a wrapper, a crate that wraps it, which leverages the Rust type system and idioms to present a cleaner and more ergonomic API. This is the crate. This crate is called seL4, and it should be seen as the real Rust libseL4, and the seL4 sys crate is almost just an implementation detail. It doesn't introduce any new dependencies, and thread local storage is still optional. Here's a quick code example. Here we're invoking untyped retyped on untyped cap. In the first example, we're using an implicit IPC buffer, which usually means the presence of thread local storage, or a global IPC buffer if you have a runtime where you don't want to implement thread local storage and you only have one thread. And down below, we're passing an explicit IPC buffer, which I guess would be useful in cases in multi-threaded runtimes that don't implement thread local storage. And I haven't come across one, but the point is it doesn't make any assumptions. So now let's talk about the Rust standard library. It's divided into 3 layers. The bottom layer, called libcore, requires virtually nothing from the language runtime or environment. The next layer, called liballoc, provides utilities like collections, but it requires a heap allocator. And the top layer, called libstud, requires, or it provides an interface to system-dependent OS services. And the bottom 2 layers are clearly useful to us. The third layer requires porting and a more rich environment than the ones we're talking about, so it's out of scope for now. There are ways to make use of that top layer in Rust Userspace for seL4-based systems, but not in any Rust Userspace code, so it's out of scope for now. And actually, this work that is now up on GitHub doesn't address it. And we exclude libstud from our code using a language feature that I'll refer to as noStud, but if that doesn't mean anything to you, you don't have to worry about it. So we have bindings for the seL4 API. We have the relevant bits of the Rust standard library, and we still need some language runtime elements. So these are an entry point, a stack, maybe thread local storage, maybe heap allocator, a panic handler, and maybe some exception handling. The implementations of many of these elements will have to depend on the program's environment. Is it a root task? Is it a microgit protection domain? Is it running in some much more rich environment, like some of the really awesome OS frameworks we've heard about so far in the summit? I've written all of this language runtime code that I'm going to talk about to be super modular, so you can assemble the basic building blocks into a language runtime suitable for your purpose. So for example, here's how we do thread local storage. Each thread already has a thread local region of memory, is the stack. So at initialization time, we reserve a region of the stack according to the TLS image, thread local storage, not transport layer security, and then initialize it with that image. And this isn't all that interesting, I would say, but it's I'm just trying to highlight that it's implemented in a modular way in its own crate. Rust supports C++ style exception handling using stack unwinding. Most noStud runtimes choose not to support it, but it's important to have in some cases for the sake of robustness and resilience. This work leverages a third-party crate that does most of the heavy lifting, so all my code really does is just wire things together. And this code example demonstrates some basic exception handling. You can wrap some code in that function called catch unwind that catches a stack unwinding and allows you to continue. And the stack unwinding does all kinds of cleanup. It drops data and whatnot. And once you can unwind the stack, you can also think about gathering backtraces for debugging. Binaries map in unwinding tables, but not debugging symbols. So you can have your program spit out raw serialized backtraces and then symbolize them on your development machine. So that's the device spitting out a raw serialized backtrace. And then on the development machine, we run a tool to symbolize the backtrace according to the debug symbols that you have on your development machine. Or if you're lazy and have lots of spare memory on your device, you can stuff debugging symbols into your binaries loadable segments and then get the program itself to spit out a symbolized backtrace. It's not really recommended in all cases, but this repo supports both ways of doing it. And I've been talking about building blocks, language runtime building blocks. I provide 2 fully assembled language runtimes, one for root tasks and one for microkit protection domains. They're both highly configurable. So let's talk about the root task runtime first. You can choose with or without thread local storage, with or without a heap, and with or without stack unwinding. It's just a crate, so it's easy to use. For example, here's a hello world root task. You just depend on the seL4 root task crate, and you use that attribute macro called root task to declare main. The macro's implementation is super simple. It's just a few lines of code, but I won't go into it right now, but feel free to ask about it. The microkit runtime is similarly configurable and easy to use. It's configurable, the same parameters. And it's a little more interesting because it implements the protection domain event loop. This example gives you a sense of how you hook into that loop. You write an initialization function that returns an event handler. I won't go into this too much because Yvonne and Ben's presentations might cover this kind of stuff, but this is just the basic skeleton for protection domain using this work. It's pretty natural and what you might expect, which is the point. And now that I've covered all that foundational code, we can start talking about higher level libraries. For example, logging, synchronization using seL4 IPC, safely accessing untrusted shared memory, the device driver framework that Lucy talked about, higher level RPC over endpoints, and perhaps most interestingly, concurrency on a single level seL4 thread. And this has been mentioned a few times in the context of Rust so far, so I'll go into it a bit. Async Rust is a concurrent programming model for lightweight green threads. It's implemented almost entirely at the library level, and the programmer is given lots of freedom for how to run and use these green threads, and we will make use of that freedom. The design is based on this future trait from the standard library. A future is a stateful computation whose status you can pull, and a stateful non-blocking computation whose status you can pull. When you call pull, the future makes as much progress as it can and then reports whether or not the output is ready. And crucially, there's machinery for signaling when a future might be able to make progress to avoid unproductive pulls. You can compose futures explicitly like in the serve function. The composition pulls receive, the composition being the body of the serve function, pulls receive until it produces a request, and then from then on it will pull send until that completes. And for languages with more powerful type systems like OCaml, this turns out basically to be enough. But with Rust, we need a small built-in language feature to get the most out of this idea. Async await is a syntax that allows us to write asynchronous code as if it were sequential. So these two are basically equivalent. I won't dwell on this, but I'll have another example in this next slide. With async await and with the runtime support I'll talk about in a sec, we can write our HTTP server request handlers using async like this. You can see it's quite a natural way to write this code, but this isn't just a normal function, it's a future, which means that it can be executed asynchronously along with many other features concurrently. We get concurrency. From this, we get concurrency all on one seL4 thread. So the HTTP server, this is a loop from the HTTP server that spawns a bunch of green threads to handle requests. And there's no syscalls here, nothing. It's just all at the library level, the Rust library level. And the server protection domain's event handler, in the microkit sense of event handler, is centered around a so-called executor. And this is a concept from async Rust. An executor is, its job is to maintain a pool of running or pending futures and to respond to external events, for example, from the drivers by pulling those futures which have been woken up. And the IP stack that we use, small TCP, which we'll hear more about later, has built-in machinery to hook into async. So when you pull the IP stack, it knows which futures it needs to wake up. So it's all the use of the pull functions is efficient. And again, all the code implementing all this is modular. The HTTP server example just demonstrates one way to use it. I know we started a little bit late. When is this? Okay, cool. So I'm taking a little more time than I expected. So maybe I'll be judicious with the rest. So I hope I've squashed any sense of mystery or wonder here. This HTTP server is just a bunch of layers of Rust code, and from the language runtime to the HTTP implementation to the executor. So I'll talk a little bit about this part, and then we'll have some questions. So also in that repository is a CapDL-based system initializer, aka CapDL loader, written in Rust. And the original purpose of this initializer was to test the seL4 crate. So I talked about how we test the seL4 sys crate. To test the seL4 crate, I thought this would be a good idea because I saw all those CapDL specs out there as just free test vectors that would cover the seL4 API way better than any manual testing feasibly could. And the Rust CapDL initializer is similar to the C one that we all know and love, with two key differences. It supports a means of mapping carefully ranged pages of the root task itself directly into protection domain vSpaces to avoid wasting unreclaimable root task memory resources. As we heard earlier, Project Sparrow supports another way of avoiding this waste with a kernel patch that's better for dynamic systems. And this approach works best is designed for static systems. Secondly, it supports a usage mode where the initializer is built ahead of time and then later coupled with the serialized CapDL spec, and I'll talk more about that in a second. Thanks to these differences, the CapDL initializer in this repo is suitable for use as the microkit initializer, the microkit CapDL initializer in cases where the verified case initializer isn't applicable. For example, on not quite yet verified configurations like ARTT4 and NMCS, or for development, thanks to how easy it is to use in a build system. This part seems kind of boring compared to what kinds of questions you all may have. But I want to just briefly mention this technique because in the build systems that we use with seL4, I think this technique has the potential to eliminate some complexity. So I'm not going to talk about it specifically in the CapDL case. Actually, I will. So the way that the C CapDL initializer is built is we have the initializer program source. We have main.c. We have the CapDL spec, which we translate into C using the parse CapDL tool. And then we compile and link those things together. And then we get the initializer with the spec. The Rust CapDL initializer in this repo supports that usage mode, which is great for code size, for just limiting the resources consumed by the root task. But it also supports one like this, where you compile the initializer, maybe a long time ago, and then you serialize the CapDL spec, and then you combine the two using a technique that I'll call ELF synthesis, and then you get your image that you actually run. So we're used to, this is what I'm calling ELF synthesis. So we're used to ELF files that are the output of compilation. The program headers present a view of the ELF file as a program image, and on the other side of things, the section headers present a more structured view of the ELF file as compilation output, with symbols and debugging information. But when we think of ELF files as inputs to seL4 related tools, for example, the ELF loader, most of that extra structure is irrelevant. And all that these tools care about is the program image, which is very simple compared to some of the other stuff in an ELF file. So I've created a simple tool that allows us to extend and patch program images by creating new super simple synthetic ELF files, which only have program headers. And for the CapDL initializer, we create a synthetic ELF file that contains the original CapDL initializer. It contains the serialized CapDL spec, and then it patches a variable in the initial program image, in the program's program image, to point to the spec. And this may sound like a hack, but I'll argue that it's actually quite a simple and good solution to this problem. And I think it has a lot of applications in our build systems here. Okay, so I'm gonna wrap it up. I'm not gonna talk about the ELF loader that's in there, because it's not really. I mean, it's more just for testing and development, and it uses the same technique. I'll briefly talk about what's next after having now that I've outlined what's in the repo. We're eager to support adoption. Use the stuff, reach out with questions, and don't be shy with the feedback. Open issues, PRs, email me, find me on Mattermost. We also want to support more configurations. We should probably do some benchmarking. We're on our way to hosting these crates on crates.io, but for now, you can use them as Git or path dependencies. We want more high-level constructs and reusable components, and I'm really excited for Ben's talk, where he'll be talking about some of the possibilities there. Yeah, so I have way less time for questions than I thought, but that always happens.
Okay, I think Brandon has the first question.
Please tell me you declared a section heading for the stuff you patched into the ELF file instead of just the segments, so that I can tell they show, so I can see them when I run object dump.
So I use the original ELF file for debugging. I don't view the synthetic ELF file as useful for debugging or inspection. It's really just input to.
But it's what actually runs on the system, right? That sounds dangerous to me. Maybe I'm being paranoid.
I view it as a way of doing something at build time that you might otherwise do at runtime. Well, we can talk about it later, but
sure.
I'm interested in this feedback, so
okay.
we'll talk about it later.
No worries.
Cool.
Thank you.
Yeah.
Quick question. Have you thought about supply chain attacks and cargo vet?
No. I assume that's a way to audit cargo dependencies and.
Yeah, it's the start of a global database of auditing that's happened on crates. Cool. I don't know what your dependencies are like.
Runtime dependencies there are very few of them, but
Right.
But built-time dependencies, there are a bunch of crates which obviously are trusted. So that sounds like an important thing to look into.
Yeah, we're headed in the direction of vendoring crates. So to guard against that, but cargo vet is also worth looking at.
Cool. Yeah, that's good.
Did you have any plans yet? Right here. do you have any plans, or maybe it's too high level, but showing examples of how you work with crates like embedded HAL, so that you have a common structure for device drivers on different platforms?
You should you'll look forward to Ben's talk. He's going to talk all about the possibilities.
Great.
There. Yeah.
All right, I think we're at time. And
Find me anytime during the rest of the conference, and we'll talk about any of this here. Email me, find me at Mattermost. Maybe there'll be a birds of a feather session about it too. Cool.
all right, thanks a lot, Nick.
Thank you.